At the end of this video, you should be able to explain how sunspots are related to powerful magnetic fields on the sun, compare prominences, solar flares, and coronal mass ejections, and describe how the solar wind can cause auroras on Earth. Chapter 29, Section 2, Solar Activity. The gases that make up the sun's interior and atmosphere are in constant motion. The energy produced in the sun's core and the force of gravity combine to cause the continuous rising and sinking of gases. The gases also move because the sun rotates on its axis. Because the sun is a ball of hot gas rather than a solid sphere, not all locations on the sun rotate at the same speed. Places close to the equator on the surface of the sun take 25.3 Earth days to rotate once. Points near the poles take 33 days to rotate once. But on average, the sun rotates once every 27 days. Sunspots. The movement of gases within the sun's convective zone and the movements caused by the sun's rotation produce magnetic fields. These magnetic fields cause convection to slow in parts of the convective zone. Slower convection causes a decrease in the amount of gas that is transferring energy from the core of the sun to these regions of the photosphere. In some places, the magnetic field is thousands of times stronger than it is in other places. Because less energy is being transferred, these regions of the photosphere are up to 3,000 degrees Celsius cooler than surrounding regions. Although they still shine brightly, these cooler areas of the sun appear darker than other areas do. These cool, dark areas of gas within the photosphere are called sunspots. The photosphere has a grainy appearance called granulation. The area around the sunspots shown on the screen here are visible granulation. A large sunspot can have a diameter of more than 100,000 kilometers, which is several times the diameter of Earth. The sunspot cycle. Astronomers have carefully observed sunspots for hundreds of years. Observations of sunspots showed astronomers that the sun rotates. Later, astronomers observed that the numbers and positions of sunspots vary in a cycle that lasts about 11 years. A sunspot cycle begins when the number of sunspots is very low, but begins to increase. Sunspots initially appear in groups about midway between the sun's equator and poles. The number of sunspots increases over the next few years until it reaches a peak of 100 or more sunspots. Then sunspots at higher latitudes slowly disappear. The new ones appear closer to the Earth's equator. The graph on the screen here shows that after the peak, the number of sunspots begins to decrease until it reaches a minimum. Another 11-year cycle begins when the number of sunspots begins to increase again.
Sunspots are cooler spots in the sun's photosphere, or the visible surface of the sun. Sunspots are still very hot. They appear dark only compared to the hotter surface around them. Sunspots are caused by intense magnetic fields that pass through the surface of the sun and out into space. Large sunspots, such as the one shown here, can be several times the size of Earth. The number of sunspots and their location on the sun changes from year to year, reaching a maximum about every 11 years. One exception occurred from the years 1645 through 1715, when sunspots were not observed.
Solar ejections. Many other solar activities are affected by the sunspot cycle. The solar activity cycle is caused by the changing solar magnetic field. This cycle is characterized by increases and decreases in various types of solar activity, including solar ejections. Solar ejections are events in which the sun emits atomic particles. These events include prominences, solar flares, and coronal mass ejections. Prominences. The magnetic fields that cause sunspots also create other disturbances in the sun's atmosphere. Great clouds of glowing gases, called prominences, form huge arcs that reach high above the sun's surface. Each solar prominence follows curved lines in the magnetic force from a region of one magnetic polarity to a region of the opposite magnetic polarity. Some prominences may last for several weeks, while others may erupt and disappear in hours. The gas in prominences is very hot and is commonly associated with the chromosphere. Solar flares. The most violent of all solar disturbances is a solar flare, a sudden outward eruption of electrically charged particles such as electrons and protons. The trigger for these eruptions is unknown. However, scientists know that solar flares release the energy stored in strong magnetic fields of sunspots. This release of energy can lead to the formation of coronal loops, such as the ones shown on the screen here. Solar flares may travel upward thousands of kilometers in minutes, but few eruptions last more than an hour. During a peak in the sunspot cycle, 5 to 10 solar flares may occur each day. The temperature of the gas in solar flares may reach 20 million degrees Celsius. Some particles from these solar flares escape into space. These particles increase the strength of the solar wind. Coronal mass ejections. Particles also escape into space as coronal mass ejections, or parts of the corona that are thrown off the sun. As the gusts of particles strike Earth's magnetosphere, or space around Earth that contains a magnetic field, the particles can generate a sudden disturbance in Earth's magnetic field. These disturbances are called geomagnetic storms. Although several small geomagnetic storms may occur each month, the average number of severe storms is less than one per year. Geomagnetic storms have been known to interfere with radio communications on Earth. The high-energy particles that circulate in Earth's outer atmosphere during geomagnetic storms can also damage satellites. They can also lead to blackouts when power lines become overloaded. Not all solar activity is so dramatic, but the activity of the sun affects Earth every day. Auroras. On Earth, a spectacular effect of the interaction between the solar wind and Earth's magnetosphere is the appearance in the sky of bands of light called auroras. The photo on the screen here shows an example of an aurora. Auroras are usually seen close to Earth's magnetic poles because electrically charged particles are guided toward Earth's magnetic poles by Earth's magnetosphere. The electrically charged particles strike the atoms and gas molecules in the upper atmosphere and produce colorful sheets of light. Depending on which pole they are near, auroras are called northern lights, or aurora borealis, or southern lights, or aurora australis. Auroras normally occur between 100 and 1,000 kilometers above Earth's surface. They are most frequently just after a peak in the sunspot cycle, especially after solar flares occur. Across the northern contiguous United States, auroras are visible about 5 times per year. In Alaska, however, people can see auroras almost every clear, dark night. Astronauts in orbit can also look down on Earth and see auroras. But Earth is not the only planet that has auroras. Spacecraft have recorded auroras on Jupiter and Saturn. At this point, you should be able to explain how sunspots are related to powerful magnetic fields in the sun, compare prominences, solar flares, and coronal mass ejections, and describe how the solar wind can cause auroras on Earth.